So, as you know, this is the second part of a joint lecture with Roberto Giuntini, mainly devoted to quantum computational logics. What are quantum computational logics? It's already mentioned by Roberto. Quantum computational logics are new forms of quantum logic that have been inspired by quantum computation. So these logics can be regarded as a natural logical abstraction from the theory of quantum circuits. Let me very briefly sketch the basic semantic ideas of quantum computational logics. In these logics, any formula, say alpha, of a quantum computational language is supposed to denote a piece of quantum information. So a density operator, say rho, living in a Hilbert space, whose dimension depends on the linguistic complexity of our formula alpha. And the logical connectives correspond to particular gates. There are different forms of quantum computational logics. Quantum computational logic is not unique. Anyway, I will refer today to the simplest form of quantum computational logic that is formalized in a sentential language. So let us call this language L. And the alphabet of this language contains atomic formulas, including two special formulas, T and F, that denote the truth and the falsity, respectively, and the following connectives. The negation connective, indicated in the usual way, that corresponds to the gate negation. The exclusive disjunction, indicated in this way, as already done by Roberto, out in Latin, and this disjunction corresponds to the gate XOR. Then we have a Toffoli connected, indicated by this different kind of T, that corresponds to the Toffoli gate. And finally, the Hadamard connective, that corresponds to the Hadamard gate. And this indicated in this way, because as you have learned in the previous lecture, the Hadamard connective is also called square root of identity. And all these connectives simulate at a syntactical level the behavior of the corresponding gates. The negation and the Hadamard connective are unary connectives which act on single formulas. The exclusive disjunction is a binary connective, and the Toffoli connective is a ternary connective. So this is the rule. If alpha, beta are formulas and Q is an atomic formula, then the Toffoli connective applied to the triplet alpha, beta, and Q gives rise to a formula. And on this basis, recalling the definition of the quantum computational conjunction, and now you know everything about this particular form of quantum conjunction, that is generally a holistic conjunction, as explained by Roberto. Recalling this definition, a binary conjunction connective indicated in the usual way can be defined in terms of the Toffoli connective. So, in the expected way, alpha and beta can be defined as the Toffoli connective applied to the triplet alpha, beta, F. And this F, that is the false formula, represents clearly here a syntactical syllable. You obtain in this way inappropriate formal logical language for the description of quantum circuits. Let us look at some particular example. You have seen the Bell circuit that can generate the Bell state. You have seen in the previous lecture the Bell state indicated in this way, that is this genuine superposition, the superposition of the register cat11 and the register cat00. And you already know that this state can be generated by the computer IBM Q by applying the Bell state circuit to the input, the register cat00. You have seen this particular register of the computer IBM Q. So mathematically, clearly, the Bell circuit can be indicated in this way. It consists of the following gates. The gate XOR, defined on the space H2, C2 times C2. The gate NOT times identity, and this is again a gate of the space H2. And finally, the gate Adamar times identity, and this is again a gate defined on the space H2. So if we apply this circuit to the input cat00, we obtain what is expected. So we obtain just the Bell state. And this is the Bell state that you have already seen in the previous lecture. So what will be the Bell formula that represents in an adequate way the Bell circuit? Let me indicate the Bell formula in this way, beta Bell. It is naturally expressed in the following way. It is the exclusive disjunction between the formula not Adamar Q and the formula Q. It is simply a representation in our formal language of what happens at the Hilbert space level. So when the input is the register cat00, in our Bell formula, we will take, in place of the generic atomic formula Q, the false formula, because the false formula denotes just the bit cat0, the truth value 0. And so we obtain the following natural correspondence. This is the Bell circuit applied to this particular input, and this is the Bell formula applied to the atomic formula falsity, a quite natural correspondence. Let me look now at a different example of a circuit. The so-called Mach-Zehnder circuit, indicated in this way, that consists of three gates, Adamar, not Adamar, and all these three gates are defined on the space H1, and the H1, let us always remember, the space H1 is the space C2. It describes a single physical system, not a composite physical system. This circuit, of course, can be implemented by our powerful IBM computer that can do many things. But one can also use a different implementation that is interesting for some reasons. An optical implementation that uses a Mach-Zehnder interferometer, where the Adamar gate is physically realized by a beam splitter, and the negation gate is realized by a pair of mirrors. So this is a Mach-Zehnder interferometer is, of course, well known to physicists. Let me very briefly recall what happens in the case of a Mach-Zehnder interferometer. We have a photon beam, possibly consisting of a single photon, and this is very important also from a philosophical point of view, in my opinion, that this photon beam can consist of a single photon. And this photon beam may move in different directions. And we conventionally assume that ket 0 represents the state of a beam moving along the x direction, while ket 1 represents the state of the beam moving along the y direction. And we refer to a beam that is moving along the x direction. This beam goes through the first beam splitter called BS1, this beam splitter of the apparatus, and as a consequence, it is split into two components. One component moves along the interferometer's arm in the x direction, and the other component moves along the interferometer's arm along the y direction. In this way, we have the two components of our beam, photon beam, and if we have a single photon, we have the two components of the superposed single photon. This is very important from the point of view of the interpretation of quantum mechanics. So what happens? The Hadamard gate applied to ket 0, by definition of Hadamard, transforms ket 0 into the following genuine superposition of ket 0 and ket 1. Then both components of our superposed beam on both arms are reflected by the mirrors. We have a mirror here and a mirror here, and both components are reflected by these mirrors. So mathematically, we have that the gate knot is applied to this superposition of ket 0 and of ket 1, and transforms, of course, this superposition into itself by definition of knot that transforms ket 0 into ket 1 and vice versa, and because the vector sum is commutative. So knot transforms this superposition into itself. Finally, the superposed beam goes through the second beam splitter, this beam splitter, BS2, which recomposes the two components. So we have the Hadamard gate applied to this genuine superposition, transforms this genuine superposition into the bit ket 0, by definition of the Hadamard gate. So what happens? That the Mach-Zehnder circuit, Hadamard, not Hadamard, applied to ket 0, gives rise to ket 0. These results, and physicists know this story very well, of course, this result, which is at the same time mathematically proven, we have proven it from a mathematical point of view, and confirmed by the experimental evidence, seems to contradict any classical physical expectation, according to which a beam that has entered into the interferometer along the x direction, after having crossed the second beam splitter, should be detected with probability 1/2 either along the x direction or along the y direction. And in fact, this is precisely what happens whenever a measurement is performed inside the interferometer box. In such a case, photons are detected either along the x direction or along the y direction with a frequency that is approximately equal to 1/2. And one can easily understand the reasons why the Mach-Zehnder experiment has been a very important object of discussion in many philosophical debates about quantum theory. But this is another story. So what will be the Mach-Zehnder formula that naturally corresponds to the Mach-Zehnder circuit? Clearly, this formula, I indicate this formula by beta mz, the Hadamard connective, the not connective, the Hadamard connective, apply to a generic atomic formula Q, and when the Mach-Zehnder circuit is applied to the input ket 0, to the bit 0, we replace our generic atomic formula Q with the false formula F, and we obtain the following very natural correspondence. So in this sense, the formulas of our quantum computational language represent an adequate description of quantum circuits. We could also see that the formulas of this particular logical language represents an abstraction from quantum circuits. Now, let me introduce a syntactical notion that will play a very important semantic role. This notion is the notion of atomic complexity of a formula. What is the atomic complexity of a given formula? Let alpha be a formula of our quantum computational language, any formula. The atomic complexity of our alpha is simply the number of occurrences of atomic formulas in alpha. The best thing is to look at a particular simple example. Consider the contradictory formula alpha, Q and not Q, and by definition of conjunction, Q and not Q is the Toffoli connective applied to the triplet Q not Q F. Q is an atomic formula. We have three occurrences of atomic formulas, Q, Q, F. So the atomic complexity of our formula alpha is simply 3, a very trivial concept. But this very trivial syntactical concept is semantically important because it determines the semantic space, let us call it H alpha, where any piece of quantum information representing a possible meaning of alpha shall live. So we can write in this way, H alpha in this particular space that is determined by the natural number that is the atomic complexity of alpha. And this is important because this gives rise to a bridge from the syntactical world, the world of formulas, to the Hilbert space world. Another syntactical notion that is very important from the semantic point of view, and as we will see also from the physical point of view, is the notion of syntactical tree of a given formula. What happens in this case? Any formula alpha of our language can be decomposed into its parts, giving rise to a syntactical configuration that is called the syntactical tree of our formula. Again, the best thing is to look at a particular example. Take again alpha as...
Marisa, sorry. There is a question by Patricia about the complexity. Please, Patricia.
Yes, please.
Hello. Hi. Yes. Well, I think Roberto already answered it.
Yes, already answered. Yes.
But anyway, maybe it's clarificatory in any case because I'd like a bit more of an answer. Maybe in the example you gave of the atomic complexity, well, Q and not Q is always false, whether Q is true or false to start with, right? So I was wondering whether the atomic complexity takes into account these possible simplifications.
The atomic complexity concerns only the number of atomic occurrences. So in this formula, what is important for the atomic complexity is the first occurrence of Q, the second occurrence of Q, and F. The fact that the Q is negated in the second case plays no role for the definition of atomic complexity.
Oh, sure. But sorry, if I've understood correctly, the Toffoli gate Q not Q false is always equal to false, no?
but we will see later what happens for contradictions in quantum computational logics, but we will see this example because in quantum computational logics, the classical non-contradiction principle is no more valid, as happens in the case of fuzzy logic. So we have the rule that if Q is true, then not Q is false. Only if Q and not Q are interpreted as classical pieces of information. But if they are interpreted as qubits, the non-contradiction principle fails. But we will see, in the semantics for this language, we will see what happens exactly for formulas of this kind. That can be implemented, interestingly enough, these forms of contradictions can be calculated by the computer IBM Q. And this is very interesting.
Sure. So can I ask a slightly more general question then?
Yes.
So even abstracting away from this particular example, I bet there are different ways of writing down the same formula. And maybe those different ways have different number of occurrences of the atomic formulae.
You know, from the syntactical, in every logic, from the syntactical point of view, a formula is a particular object. What you have written, a formula, syntactical sequence of symbols. So a formula is unique. But what is semantically interesting is studying the possible logical equivalence between different formulas.
That makes sense.
Logically interesting. But by definition, a formula is a particular sequence of symbols.
Cool.
So the formula is unique.
Sure, that answers my question perfectly. Thank you.
Please. May I go on? And so may I go on?
Yes, sure, Marisa. Thank you very much for the clarification.
So we take now this particular formula, this contradiction. What is the syntactical tree of this formula? It is a sequence of levels. In this particular case, level 3, level 2, level 1. And each level is a sequence of sub-formulas of our formula. The bottom level, level 1, is the sequence that contains our formula, toffoli of Q, not Q, F. The top level, in this case, the top level is level 3, is the sequence that contains the atomic formulas occurring in alpha. So Q, Q, F. And each level, I plus 1, is obtained by dropping the principal connective in all molecular formulas occurring at level I, and by repeating all atomic formulas that occur at level I. So let us look at this particular case. Here we have the formula toffoli of Q, not QF. We drop the principal connective that is toffoli in this particular case. So we obtain 3 formulas, Q, not QF. Q and F, the first Q and F, are atomic formulas that cannot be decomposed into other parts. So we repeat here at level 3, this particular occurrence of Q, but here we have a connective, the principal connective of our formula, not Q. We drop this not. Finally, at the top level of our syntactical tree, we obtain the sequence Q, Q, F. And we will later see why this pure syntactical game will be important from the semantic, and we'll see also from the physical point of view in the theory of circuit. But what happens? The syntactical tree of any formula alpha uniquely determines a quantum circuit, a sequence of gates all defined on the semantic space of our formula alpha. And we call such sequence the gate tree of alpha. We might say also the circuit of alpha. Perhaps the circuit of alpha would be a better terminology, by the way. Let us consider again our contradictory formula. In this talk, we like contradictions. So Q and not Q, that is thoughtfully applied to Q, not QF. This was the syntactical tree of our formula. The second level of the syntactical tree of our formula has been obtained from the third level by repeating the first occurrence of Q, by negating the second occurrence, and by repeating F. So it is very natural to assume that the gate that corresponds to this syntactical operation is the following gate: identity times not times identity. And this product gate is, of course, a gate defined on the space H3, that is the semantic space of our formula. Then finally, at level 1, we have applied the Toffoli connective to the triplet of formulas occurring at level 2. And so it is very natural to associate to this particular formula the Toffoli gate applied that lives in the space H3. The space H3 is C2 times C2 times C2. So the gate tree of our alpha can be represented in the natural way. Let us write C of alpha. It is a sequence of two gates, these two gates, this and this. So identity times not times identity, and Toffoli. Well, and now we can turn to semantic notion. We consider a holistic and contextual version of the quantum computational semantics. You have heard in the previous lecture why holism is so important in the quantum theoretic formalism, and also contextuality is very important. As is well known, this is not the case in classical semantics, because classical semantics is essentially compositional and context independent. Let me very briefly recall what happens in the case of classical semantics, where in the case of sentential classical logic, things are very, very simple. We'll see that the case of sentential quantum computational logics is a little bit more sophisticated. You know that in all logics, from the semantic point of view, the basic concept is the concept of model or interpretation of the language. So what is a classical model or interpretation in the case of a sentential language for classical logic? It is simply a function v that assigns to any formula alpha a truth value, either 1 or 0, according to the following rules. The interpretation v assigns to an atomic formula Q a truth value, either 0 or 1. Then v assigns to a negated formula, not alpha, the Boolean complement of the value of alpha. And v assigns to a conjunction, alpha and beta, the Boolean infimum or meet, as you want to call it, between the two values of alpha and beta. And you know that in classical logic, it is sufficient to consider two connectives, for instance, negation conjunction, because you have only heard about universal, about the fact that, for instance, negation and conjunction are functionally universal. So from the syntactical point of view, we need only the connective conjunction and the connective conjunction and the connective negation, because all other connectives can be defined in terms of negation and conjunction. This semantics is compositional. Why compositional? Because the meaning, a meaning here means truth value of any formula, is a function of the meanings of its parts. And it is also context independent, because for any formula alpha and any context represented by a formula gamma where alpha occurs as a subformula, we assigns to alpha one and the same meaning. So meanings are context independent in classical semantics. And the classical concept of logical consequence is very natural and simple in the case of a sentential language. By definition, a formula beta is a logical consequence of a formula alpha, indicate usually in this way. If and only if, for any model, any interpretation of the language, if the considered interpretation assigns to alpha the truth value 1, then the interpretation assigns to beta the truth value 1. So whenever alpha is true, also beta shall be true. This is a very ancient concept of logical consequence that goes back to Greek logic. This condition is, of course, equivalent to the fact that since we have two true values, that the truth value of alpha is less than or equal to the truth value of beta. And now let us turn to our quantum computational semantics, that is a little bit more complicated. Also here, the basic notion is the notion of model, but we will speak here of holistic model, because our semantics is holistic. And the concept of holistic model of the language, of our quantum computational language with the connectives that we have seen before, this concept of a holistic model is based on a weaker notion, the notion of holistic map. What is a holistic map? It is a map that assigns to each level of the syntactical tree of any formula alpha of the language a global meaning represented by a density operator living in the semantic space of alpha. Because in these semantics, meanings are density operators, because they represent possible states of quantum systems that can store the information in question. This has been mentioned by Roberto at the very beginning of his talk. So we can write in the following way: a holistic map assigns to each level I of the syntactical tree of alpha a density operator that lives in the semantic space of our formula alpha. And on this basis, the meaning that the holistic map whole assigns to a formula alpha can be identified with the meaning that whole assigns to the bottom level of the syntactical tree of alpha. Alpha has a syntactical tree. The bottom level, level 1, is the sequence that contains alpha only. So it is natural to identify the meaning that whole assigns to alpha with the meaning that whole assigns to the bottom level, to level 1 of the syntactical tree of alpha. And now, in this semantics, a very important role is played by the notion of contextual meaning. Contextual meanings do not exist in classical semantics, but also in other forms of semantics, for instance, in the intuitionistic semantics. But contextuality, we know, is very important in quantum theory. Contextuality is a basic feature of the quantum theoretic formulas. So in this particular semantics, it is interesting to consider contextual meanings. So given a formula alpha, any holistic map whole determines the contextual meaning with respect to the context whole alpha, that is a density operator. Whole alpha is a density operator. Contextual meaning with respect to the context whole alpha of any occurrence of a subformula beta in alpha. Now, in order to define a reasonable concept of contextual meaning, it is very natural to use the notion of reduced state. You have seen with Roberto what is a reduced state. If we have a composite system whose state is a given density operator rho, this composite system consists of some parts. The state rho determines the states of the parts, and these states of the parts can be calculated by means of the notion of reduced state that play an important role in the quantum theoretic formulas. And now, in our semantics, it is natural to use this particular quantum notion. Suppose that our formula alpha has the following height level in its syntactical tree. So the height level of the syntactical tree of alpha is the following sequence of occurrences of subformulas, BI1 and so on until BIR. We want to define the contextual meaning of a given occurrence. Let us call it Bij. So Bij is the jth occurrence of the subformulas that occurs at the height level of the syntactical tree of our formula. So we want to define the contextual meaning of this particular occurrence, beta ij, with respect to the context whole alpha, and whole alpha is the meaning of our whole formula alpha. And in order to do this, we naturally use the notion of reduced state. So this is the definition. The contextual meaning with respect to the context whole alpha, that is the meaning of alpha, of the occurrence beta ij is the reduced state with respect to the jth subsystem of the density operator that the map whole has assigned as a meaning to the level I of the syntactical tree of our formula. Perhaps this is an important concept. Perhaps I should repeat it. Anyway, let me repeat it. The contextual meaning with respect to the context whole alpha of this particular occurrence of a subformula of alpha, this is the jth occurrence at the ith level of the syntactical tree of alpha. So we look at the density operator that represents the meaning of the whole level I of our syntactical tree of our formula. And this is the meaning, that whole, the density operator, that whole has assigned as a meaning to level I. And then we take the reduced state of this particular density operator, whole of level I of alpha, the reduced state with respect to the J subsystem. And this seems to represent a quite natural semantic notion of contextual meaning. And now we need a general concept of holistic model. And the concept of holistic model of our language can be defined as a holistic map that satisfies some natural logical restrictions. So this is the definition. A holistic model of the language L is a holistic map whole that satisfies the following condition. First of all, whole preserves the logical form of any formula alpha in the following sense. The meaning of each level, level I of the syntactical theory of our formula, different from the top level, is obtained by applying the corresponding gate, Gi, of the gate tree of alpha, to the meaning of the level that occurs immediately above, so level I plus 1. So this is the formal condition. Whole assigns to level I, not any possible density operator that lives in the semantic space of alpha, but this particular density operator that has been obtained by applying the gate Gi that occurs at step I in the gate tree of alpha to the density operator that represents the meaning that whole has assigned to the level of the syntactical tree that occurs immediately above. So an important role is played here by the gate tree of our formula. Why? Because the gate tree of a formula contains the gate that interpret the corresponding logical connectives that occur in our formula. So this condition means the following, that the logical form of any formula is preserved by the map that shall be a holistic model. The second condition is also very natural. It is the following. Whole size.
Sorry, Marisa.
See?
A question for you. Clarissa Lee has a question for
Yes.
you. Clarissa, please.
See? Please?
Hi. Yeah, sorry to interrupt. I was just looking at your explanation of the holistic model, the holistic map. I'm just curious to understand, like, for each of the atomic alphas, whether the levels that you indicated, the hierarchies, the L3 to L1, are they all contextually dependent in the sense they cannot exist independently of each other? So what happens in one level is dependent on what happens on the level before, right? And they are kind of like nested downwards, right? And this is a very particular context of quantum logical connectives.
Yes.
And it's part of the Toffoli connective, right?
Yes. Perhaps we should see the whole definition and then perhaps go back, because we have seen here only the first condition. If we see also the second and the third condition, then perhaps all the story is more clear. The second, I will go back to your question. The second condition requires that whole assigns the same contextual meaning to different occurrences in the syntactical tree of our formula of one and the same subformula of alpha. So what is required here? In the framework of a given formula, each subformula preserves the same contextual meaning. The contextual meaning does not change in the framework of a given formula. Third condition, the contextual meanings assigned by whole to the true formula T and to the false formula F are respectively the truth. You have learned that the projection P1 represents the truth and the projection P0 represents the falsity. So it is very natural to require that T and F, these two special atomic formulas, have the right meanings. They mean the truth and the falsity, respectively. Now, let me go back to your question. What happens in these semantics? It's not so easy. It is a somewhat sophisticated concept. A holistic map assigns a meaning to any level, so a global meaning, a global meaning. Then this global meaning for each level determines the contextual meanings of all subformulas of the formula under consideration. When you consider the top level of the syntactical tree, where the only formulas that occur are atomic formulas, so the typical form is Q1, Q2, and so on until a given QR. Also, these atomic subformulas will receive a contextual meaning. The contextual meaning is determined by what whole does to each level of the syntactical tree of our formula. We go from the global meaning of each level to the particular contextual meanings of all subformulas that appear in the different levels of the syntactical tree of our formula. Is this clear or not so clear?
Yeah, thank you.
Is this sufficient? Anyway, we will see some examples, and perhaps with examples, all the story will be more clear.
Yeah, sure.
Suppose that whole alpha is a pure state, a genuine superposition, whose form is the following genuine superposition where all amplitudes are different from zero. Now it is interesting to try to interpret such a situation. From an intuitive point of view, whole alpha, that is a particular density operator, that is a pure state in this case, living in the semantic space of our formula, can be regarded as a kind of vague, ambiguous idea that alludes to other ideas represented by the pure states psi1, psi2, and so on, psi-n, that are in a sense all coexistent. Why we can give this interpretation? Because you know that in the quantum theoretic formalism, coexistence is a fact that belongs to the interpretation of pure states. If you have a pure state, psi equal to this superposition, we know that it's very natural to interpret this situation in the following way. Let us read here psi instead of whole alpha. Psi is C1 of psi1, and so on and so on. What does it mean, this, according to the standard interpretation of the quantum formalism? That we are describing a system using the pure state psi, but our psi might become psi1, psi2 with the probability that is determined by the Born rule. So in a sense, also in the case of pure quantum mechanics, not only in the case of quantum information and in the case of quantum computational semantics, the component of a quantum superposition are in a sense all coexistence. Because a superposition, after all, from an intuitive point of view, represents a kind of cloud of possibilities. And so it is natural, we will see some applications of the quantum computational logics. It is natural to use quantum computational semantics in order to apply these semantics to semantic situations even far from microphysics, where, for instance, allusion play an important role. Allusion, vagueness, ambiguities, and so on, and so on. So this is an intuitive interpretation that turns out to be useful in the case of many applications of the quantum computational semantics. We should notice that any meaning whole alpha, density operator, let us always remember that whole alpha represents a density operator, possibly a pure state, possibly a classical piece of information, possibly a classical register or a classical bit. So any meaning represents a kind of autonomous semantic context that is not necessarily correlated with the meanings of other formulas. Generally, in these semantics, one and the same formula may receive different contextual meanings in different contexts, as in fact happens in the case of our normal use of natural languages. We know this situation. Meanings, the contextual meaning change in our natural language. So the characteristic holistic features of our model whole are clearly due to the fact that any model whole assigns to each level of the syntactical tree of a given formula a global meaning that determines the contextual meanings of all sub-formulas occurring at that level. And generally, this global meaning cannot be represented as the tensor product of the contextual meanings of the sub-formulas in question. So we can say that the meaning of the whole determines the meanings of its parts and not the other way around. Against the compositionality principle, and this fact has been already noticed by Roberto in his lecture, we recover here this important feature of the quantum theoretic formalism at a semantic level. And formulas may also have entangled meanings. This is very interesting. What happens when a formula has an entangled meaning? Consider again a formula that we know very well now, the Bell formula, the exclusive disjunction between the formula not Hadamard F and F. Excuse me, I shall drink some water. So this is our Bell formula. What happens if we take a model of this form? By definition of model and of all our semantic concepts, we shall apply the Bell circuit to the meaning that our model whole has assigned to the top level of the syntactical tree of our Bell formula. And if we take the Bell circuit that we already know, and we apply the Bell circuit to the input ket 0, 0, we obtain the following result. Hence, as expected, we can conclude that our model whole assigns as a meaning to the Bell formula the Bell state. But consider a different example. Our contradictory formula, and this is connected to some of the questions that have been raised before. Consider again our contradiction Q and not Q, that is thoughtfully applied to Q, not QF. And let whole be a model that assigns to the top level of the syntactical tree of our formula alpha, our contradiction, the following entangled state. This is an entangled state that lives in the space H3, C2 times C2 times C2, a superposition of the register cat 100 and the register cat 010. This is possible in this semantics because it's not forbidden to assign to the top level of the syntactical tree of a given formula an entangled state. So the gate tree of this formula, we already know the gate tree of this formula. It is a sequence of two gates, identity times not times identity and thoughtfully. So if we want to calculate the result, we shall apply our circuit, our gate tree, to our input, and this was our input. And as a result, we obtain the following entangled state, a genuine superposition of the register cat 111 and cat 000. An important thing to notice in this particular case, now we have an entangled state that is a meaning of our contradictory formula. We shall notice that both occurrences of the atomic formula Q in our contradictory formula alpha receive the same contextual meaning in the context whole alpha. And this contextual meanings is a proper mixture. If we calculate, we obtain that the contextual meaning of the atomic formula Q in the context whole alpha is the proper mixture 1/2 of the identity. And Roberto has already mentioned a very similar situation. Here we can look at a semantic version of a situation, of a quantum situation that has been already considered by Roberto. And what is interesting is that if we calculate the probability of the meaning that whole has assigned to this particular contradictory formula, Q and non-Q, we discover that this probability is 1/2. So in this semantics, a contradiction may have probability value 1/2. The non-contradiction principle is no longer valid in quantum computational logics, as happens in the case of fuzzy logics. Contradictions are not necessarily false. And interesting enough, and this in our opinion, Roberto's and my opinion, this result, it is very interesting that this result is confirmed by the statistical measurement performed by the computer IBM Q. You have learned you have seen in the lecture by Roberto how these statistical measurements are performed by the IBM computer. Roberto himself has performed this measurement, obtaining some statistical results. And these statistical results performed by the IBM Q computer confirm violations of the non-contradiction principle. So this, let me say, is a strong result against the universality of classical logic. And now, let me define the concept of truth and of logical consequence in this particular form of quantum computational logic. A formula alpha, a generic formula alpha, is called true in a model whole if and only if the probability of the meaning the whole assigns to alpha is 1. Beta is called a consequence of alpha in the model whole if and only if for any formula gamma such that alpha and beta are subformulas of gamma, and for any model whole, the probability that of the contextual meaning of alpha with respect to the context whole gamma is less than or equal to the probability of the contextual meaning of beta with respect to the same context. So this is a somewhat sophisticated concept of logic, of consequence. You remember the concept of logical consequence in the case of classical semantics is very simple. This is not a simple concept. The concept of true is clearly probabilistic. It is a probability. Truth means having probability 1. So we are perfectly in the framework of a probabilistic semantics where probabilities are quantum probabilities, are not classical probabilities, are quantum probabilities. And the notion of consequence is a probabilistic and contextual concept because we shall refer not simply to the meaning of beta and of alpha, but instead to the contextual meanings of alpha and beta with respect to any possible context where alpha and beta may appear as subformulas. Perhaps I might repeat this concept that is a little bit complicated. Beta is a consequence of alpha in the model whole when for any formula gamma such that alpha and beta are subformulas of gamma, and for any model whole, the probability of the contextual meaning of alpha with respect to the context whole gamma is less than or equal to the probability of the contextual meaning of beta with respect to the same context. And then we say that beta and alpha are probabilistically equivalent in the model whole when beta is a consequence of alpha in the model whole and vice versa. And finally, we arrive to a concept of logical consequence. We say that beta is a logical consequence of alpha if and only if beta is a consequence of alpha in any model whole. And now we have a concept of logical consequence. And as happens in the case of any logic, once we have a concept of logical consequence, we have a logic, because a logic is semantically characterized by a particular concept of logical consequence. So we call holistic quantum computational logic the logic that is semantically characterized by this particular concept of logical consequence. And what kind of logic is this logic? One is dealing with a very weak form of logic, where many important logical arguments, valid not only in classical logic, but also in Birkhoff and von Neumann's quantum logic, are violated. You know that Birkhoff and von Neumann's quantum logic is the first form of quantum logic that has been proposed by Birkhoff and von Neumann in the celebrated paper, The Logic of Quantum Mechanics. This logic, this historical form of quantum logic, is different from the holistic quantum computational logic, because many logical arguments that hold in Birkhoff and von Neumann's quantum logic are violated in our holistic quantum computational logic. So this is a very poor logic, very weak logic. For instance, the conjunction is generally non-idempotent in this logic. Alpha does not imply alpha and beta. Non-commutative. Alpha and beta does not imply beta and alpha, and even non-associative. And this can be explained by recalling the contextual behavior of quantum meanings, because it may happen that the probability of the contextual meaning of a conjunction alpha and beta with respect to the context whole gamma is different from the probability of the contextual meaning of beta and alpha with respect to the same context, and this can be easily calculated. One can ask, but why this extremely poor form of logic? Is so a poor and weak form of logic really useful? In our opinion, yes, because this form of quantum semantics, in fact, seems to be in agreement with a number of informal ways of reasoning, where conjunctions are frequently used as non-idempotent, non-commutative, and non-associative logical operations. We all know examples of this kind. But of course, and this is very important, the holistic quantum computational semantics does not forbid semantic situations that may be compositional and or context independent. A compositional and context independent quantum semantics can be described as a particular case of the holistic quantum semantics, where any model whole shall satisfy the two following conditions. First condition, context independence. This condition asserts that for any formulas alpha, beta, gamma, the contextual meaning of gamma with respect to the context whole alpha is equal to the contextual meaning of gamma with respect to the context whole beta. In other words, whole assigns to gamma one and the same meaning in all possible contexts, as happens in the case of classical semantics. Compositionality. Compositionality can be, in these semantics, formulated in the following way. For any formulas alpha such that the top level of the syntactical tree of alpha, and the top level is a sequence of atomic subformulas, so Q1, Q2, and so on until QR. The following situation is the case. Whole assigns to this top level, consisting of these atomic formulas, a factorized state. And this factorized state is a tensor product between the contextual meaning of Q1 with respect to the context whole alpha, and so on, until the contextual meaning of QR with respect to the context whole alpha. So the meaning of the top level is a factorized state consisting of contextual meanings of atomic formulas. And on this basis, one can prove that the meaning of any formula can be represented as a function of the meanings of its atomic subformulas, precisely as happens in the case of classical semantics, but not only the case of classical semantics, also in the case, for instance, of the intuitionistic semantics or in the semantics of other, let me say, standard logics. One can prove that the logic characterized by the compositional quantum semantics is stronger than the logic characterized by the holistic quantum semantics. For instance, in this logic, conjunctions are always commutative and associative, but generally non-idempotent, as happens in the case of fuzzy logics, where one uses to say that repetita juvant, repetitions are useful, so alpha is not equivalent to alpha and non-alpha. Repeating alpha is useful, and this happens also in our particular logic, even in the compositional case. A quantum version of classical semantics can be now represented as a special case of the compositional and context-independent quantum semantics that shall satisfy the two following conditions. First condition, the language shall contain only the classical connectives, so the negation, the exclusive disjunction, and the totally connective. No Adamar. Adamar is only quantum, cannot exist in classical semantics. Second condition, for any formula alpha and any model whole, the meaning assigned by whole to the top level of the syntactical tree of alpha is a register, so a classical piece of information. Consequently, the meaning of any formula corresponds to a classical piece of information, a sequence of bits. So this is very important in our opinion, as stressed also by Roberto in the case of classical and quantum computation. The holistic quantum computational semantics is not against the classical semantics. It is simply more general than the classical semantics. And the holistic quantum computational semantics includes, as a particular case, the classical semantics. So we have obtained a very weak logic, but a weak logic that can be useful for many applications, because we know that the semantics of natural languages, for instance, is essentially holistic and contextual. We need only think how children learn their mother language, showing an extraordinary capacity of understanding and using correctly the contextual meanings of expressions that occur in different contexts. And it often happens that the meaning of a global expression is grasped by children and used in a clear and correct way, while the meanings of its parts appear more vague and ambiguous. Now, different forms of holistic quantum computational logics can be applied to investigate semantic phenomena, even very far from microphysics, where holism, contextuality, and ambiguity play an important role. As happens in the case of natural languages, as we have seen, but also in the languages of art, for instance, in the case of poetry and music. And by the way, with Roberto and with two musicians, Riccardo Luciani and Eleonora Negri, we have tried to apply this particular form of quantum semantics inspired by quantum computation to an abstract analysis of musical languages, and you can find a survey of this application in this book. And now I would like to discuss a particular problem that perhaps concerns the problem of epistemic or possible epistemic interpretations of quantum computation, but in a very particular sense in my application. It may be interesting to reflect about the changing epistemic states of a computer user, say Alice, who is performing a computation by means of a classical or even a quantum computing machines. What happens at the initial step of the computation? At the initial step, Alice is informed about the sequence of operations she wants to apply and about the input of the computation. Example, a very simple example, the sequence of operation might be represented by a polynomial like this, and the computation input might be this particular triplet of natural numbers. Notice that Alice, as a computer user, might be completely ignorant about the precise mathematical definitions of the operations sum and product. This happens very frequently in practical life. The only information Alice needs is a symbolic syntactical configuration for the operation sequence and for the input. We know now that any operation sequence corresponding to a numerical polynomial, P and so on, can be represented as a reversible quantum circuit, which in turn can be described by a quantum computational formula. So alpha corresponding to the circuit that has been associated to a given polynomial. And this alpha can be expressed in the classical part of a quantum computational language. In the case of a quantum computer, this formula alpha C associated to a circuit C might be a genuine quantum formula. For instance, it might be the Bell formula. Why not? Thus, we can assume that an ideal counterpart of Alice is informed about a quantum computational formula having this standard form, alpha of Q1, Q2, QR, and an input represented by a register, or more generally by a Q register, or perhaps even by a density operator or a genuine mixture. What happens to Alice at the intermediate steps of the computation? Both the real and the ideal Alice, who is less ignorant with respect to the original Alice, simply wait, letting the machine work. Either Alice is not necessarily aware of the mathematical content of the circuit. This is the gate 3 that represents the mathematical circuit. At the same time, the correspondence between formulas and gate trees has been established in the framework of a meta-theory, as we have done, based on the quantum theoretic formalism. Thus, we can metaphorically refer to a kind of ideal meta-mathematical epistemic agent, say Bob, for instance, us. We might be Bob in this particular case. We are informed about the gate theory of the formula alpha. In principle, Bob might be able to apply step by step all gates of the circuits, that is the gate theory of our formula alpha, starting from the input. Consequently, Bob might be able to prove that the alpha circuit applied to the input psi gives rise to the output phi. However, such a human computation might be too boring or too hard, requiring a very long time, and Bob, as well as Alice, has chosen to entrust the computation job to a machine. And this requires a physical computation. Roberto has already used this notation. This represents a physical implementation for the mathematical circuit C. So this is a mathematical object. This described physical implementation, so a hardware. For instance, the physical circuit that can implement a computation for the Bell formula, that we have denoted in this way, might be just the IBM Q Bell state circuit. Remember, this was the IBM Q Bell state circuit. And this is a physical circuit implemented by this kind of quantum computer. Of course, Bob is not necessarily aware of the physical circuit CPH that is implementing his mathematical circuit C. Normally, we are not aware of physical circuits when we do a computation. In many respects, using a classical or a quantum computer gives rise to similar epistemic behaviors. But the crucial difference between the classical and the quantum case emerges when the reading of the final output and the possibility of reading all intermediate outputs come into play. As is well known, from an intuitive point of view, a classical computer can be regarded as a box that is in principle perfectly transparent. Each intermediate output, as well as the final output, can be read by Alice, in the classical case, without disturbing the computation process. Such a transparency is instead generally impossible in the quantum case. We have seen the Mach-Zehnder circuit implemented by a Mach-Zehnder interferometer. We know that in this case, the Mach-Zehnder circuit transforms the input ket 0 into itself, the input ket 0. Hence, all outgoing photons from the interferometer box are detected along the x direction. But suppose we observe inside the interferometer box. In this way, we perform a quantum measurement that destroys the superposed state of the photon beam. And in such a case, we obtain a different output. The outgoing photons are detected either along the x direction or along the y direction with approximate frequency equal to 1/2. As is well known, in quantum theory, measurements are governed by the collapse of the wave function principle. Soon after a measurement, a superposition state is transformed into an element of the Hilbert space basis, which is associated to the apparatus that performs the measurement in question. Thus, in quantum computation, measurement transforms Q register or density operators into registers. So what happens to Alice at the final step of the computation? At the final step of the computation, Alice shall read the output. And in the quantum case, reading is an action that implies a quantum measurement. Suppose that the alpha circuits applied to the input psi gives rise to the output phi that is the following genuine superposition, where these are registers that belong to the computational basis. So this is a genuine superpositions of elements of the computational basis. After Alice's measurement, by collapse of the wave function, we have that this genuine superposition has been transformed into a particular register. Accordingly, in order to obtain an experimental result that approximately reproduces the probabilistic prediction of the superposition, this superposition, Alice shall repeat her measurement a given number of times, always using equi-prepared input states. And this is what actually happens in the case of the computations performed by the computer IBM Q, and this is exactly what Roberto has done even this morning, as far as I have understood. So in the case of the IBM Q Bell state circuit, this was the circuit, and at the end of the circuit, a measurement has been performed. This measurement, in a very intuitive way, is indicated by this figure. So at the end, we have a measurement that destroys any possible superposition and transforms superpositions into registers. Notice that our Alice cannot be theoretically informed about superposition, about this genuine superposition, that she has never epistemically reached. While in the classical case, a self-reading of a machine is in principle possible, in the quantum case, any reading of the result of a computation generally requires an external observer, and such observer is, of course, not necessarily human. In conclusion, at the initial step of the computation, Alice is informed about a syntactical formula which describes the operation that shall be performed, and about the computational input, which can be also described as a syntactical configuration. At the final step of the computation, Alice is informed about the computation output, and in the quantum case, the output is obtained by means of a quantum measurement.